Experts in many domains learn to selectively pick up relevant information, discover important patterns, and see key structure in new cases or situations. This process is known as perceptual learning. Think of the chess master who can at a glance see the good moves on a chessboard, or the expert pathologist or radiologist who knows, at a glance, whether a patient is in trouble or in the clear. Experts in these domains and others have learned to see information and patterns that to a beginner may appear invisible, meaningless, or confusing. In research on perceptual learning, we say that experts have learned to recognize patterns and perceive complex structure. The chess master, radiologist, even an artist or an athlete are united by this skill. In mathematics, for example, students are ordinarily taught explicit facts, concepts, and procedures. But there have not yet been effective ways to teach students the skill of seeing structure in math. These skills involve knowing how to classify and recognize problem structure, choose appropriate procedures, and to do so fluently so that basic information extraction does not overload complex problem solving. When students extract structure quickly and fluently, this frees up attention for higher level problem solving. Through recent research, we now know how to teach and accelerate the development of perceptual learning. Perceptual learning is targeted with interactive trials that tune the learner's ability to pick up perceptual structure. Learning develops over many short classification episodes. Exposure to appropriate examples is manipulated so that students see invariant common features across varying instances. Ideally, examples never repeat. Rather, closely related examples alternate to encourage students to see abstract structure. Accuracy feedback ensures students are discovering relevant perceptual patterns. In our work, perceptual learning technology is complemented by powerful adaptive learning technology. Our adaptive algorithms use each individual learner's response speed, as well as accuracy in interactive learning, to optimize spacing and sequencing, making learning more efficient. These adaptive techniques, implemented in digital technology, also make possible unprecedentedly rich assessment, allowing detailed tracking of all components of learning, and guiding of each student to comprehensive mastery.
A Perceptual Adaptive Learning Module, or PALM, is a piece of software that accelerates perceptual learning for a given subject using short, interactive problems, objective mastery criteria, and adaptive learning algorithms. We also refer to these as PLMs. UCLA and the University of Pennsylvania have developed 3 PLMs that teach students to see structure and relations in mathematical problems and representations. These PLMs were developed with a development grant from IES's Cognition and Student Learning Program. On the basis of strong and long-lasting learning gains with middle school students, the PLMs are now being tested in a randomized controlled trial in an IES-funded efficacy and replication study. The Slice and Clone PLM helps students understand fractions as quantities. Students must slice a given quantity to extract a unit that can be cloned to create a new quantity. First, the student must figure out how to partition the original block at the top, and then slice it using an interactive slicing tool to extract an appropriate unit. Once they've created a unit that will work, the interactive cloning tool becomes activated at the bottom of the screen, allowing them to multiply the unit to create the new quantity. As they carry out their actions on many different fractional quantities, the software provides real-time animated illustrations of the results and describes each action with a corresponding multiplication or division number sentence. Students gain fluency by moving between proper and improper fractions, multiple integers, and mixed numbers. They also learn to relate equivalent fractions with different denominators. The start-to-end PLM focuses on units of linear measurement. Many students in the U.S. don't understand the structure of units and subunits on rulers, and they make systematic errors, such as counting hash marks starting with 1 when they are measuring. By directing a ball around the screen to different points and distances, the student can overcome conceptual difficulties in understanding the properties of measurement units, the attributes they measure, the relationship between whole units and subunits, and the use of measurement tools. In the Area Measurement PLM, students practice creating two-dimensional measures of rectangular area from linear dimensions, as well as extracting linear dimensions from area arrays. This helps them conceptualize the relationship between linear dimensions, like height and width, and the units of area measurement. Interactive on-screen tools, such as clickable rulers, enable students to interact directly with linear and area units. On-screen animations help them visualize the structures and provide immediate feedback. Students also practice recognizing and properly labeling the kinds of units used for linear dimensions and area dimensions. Animations illustrate how one-dimensional linear units combine to create an array of two-dimensional area units. Throughout the learning session in each of these PLMs, students gain mastery levels as they demonstrate accurate and fluent responses to each type of problem category. Learning to objective mastery criteria ensures that all students reach full proficiency. Perceptual learning technology applied to mathematics has already shown great promise. Research on perceptual learning and its applications has broad potential to improve mathematics and science learning by allowing students to discover relevant structures and patterns, recognize these in novel contexts, and develop information selection and fluency that enable further learning.